Thanks to the organizers for inviting me and for coming. This is memory bounds for the experts problem. This is a joint work with Vaidehi Srinivas, Neil Xu, and Samson Zhou. So let me define the experts problem for you. So this is a problem of online learning or sequential prediction. So we have some number of experts. These are just people with opinions. They're don't necessarily have any expertise. And we have a sequence of days. So here's the first day. And each of the experts is going to make a prediction on this day. And we're going to focus on binary predictions for this talk. So here, each expert might say that it will be sunny or rainy on this day. You look at the expert predictions, and you come up with your own prediction. And then you see the actual outcome on that day. Okay, so in this case, it was sunny. Then you move on to day 2, and you see the expert predictions again. And maybe you use some information about the past. Maybe some experts might be less reliable than others, and you might not pay as much attention to them. You have some algorithm, and you use that algorithm to make your next prediction. And then you see the actual outcome, and so on. Okay? So this repeats for some number of days. And we're going to, we want to make the correct prediction on as many days as possible. And the way we're going to measure performance formally is we'll make no distributional assumptions. Instead, we'll use the standard notion of regret. What does this mean? Well, we're going to try to minimize the following quantity: the number of mistakes our algorithm makes more than that of the best expert in hindsight. Okay, so if we look at the best expert makes some number of mistakes, we don't want to make many more than that, and we normalize by the number of days. Okay. So in this example that I had, these red boxes indicate errors. We see that one of these 4 experts only made an error on 1 day, so that's the best expert. Our algorithm made an error on 2 days. So our regret is 2 minus 1 divided by the number 4 of days. It's 1/4. Okay? Okay, so formally to set up this problem, we have n experts who each decide for this talk on a binary outcome, 0 or 1, on each of t days. And the algorithm sees the expert predictions, and then it makes its own prediction on each day. And then it sees the outcome, and it can use this information on future days. It can store some information, use it to make its predictions on future days. The cost of the algorithm is the number of incorrect predictions, and as I said, we want to minimize the regret, number of mistakes we make, minus the number capital M of the best mistakes of the best expert divided by t, the number of days. Okay, so just notation, n is the number of experts, t is the number of days. The experts problem and techniques for solving it are used in many different places in computer science and machine learning. So it's used in ensemble learning, portfolio optimization, online convex optimization, much more broadly.
Sorry, you can remember like store in memory like all the predictions of the experiment made so far, or you have bounded memory? Or?
Oh, I'm sorry, I'm clicking the wrong thing. Yeah, that's exactly the question we're going to look at. So far, I'm just talking about the classic setting where there's no memory constraints. Yeah. Okay, so how do you solve this problem classically in the offline setting without memory constraints? So an old algorithm, weighted majority algorithm due to Littlestone and Wormuth, is you initialize a weight of 1 to all of the experts, and then what happens is when an expert makes a wrong prediction on a day, so this expert was wrong on the first day, then we downweight them by some factor. Let's call that factor 1 minus epsilon. This was the only incorrect expert on this day. On this second day, this guy was incorrect, so we multiply their weight by 1 minus epsilon, and so on. So we're paying less attention to them. Epsilon is a parameter between 0 and 1. And how do we actually make our prediction? Well, we just add up all the weights corresponding to sunny And if that's larger than the sum of the weights corresponding to rainy, then we predict sunny. Okay, so just the weighted majority. Okay. And there's a standard guarantee for the weighted majority algorithm, which is the number little m of mistakes made by this algorithm is at most 2 plus epsilon times capital M, the number of mistakes made by the best expert, plus 2 divided by epsilon natural log of n. Okay, again, epsilon is a parameter that you can adjust. But this deterministic algorithm will get at best a 2 approximation. Right? And the proof is a very short potential argument. So you just look at the sum of all the weights. On the one hand, it's at least the weight of the best expert, which is at least, it starts off at 1, and the best expert makes capital M mistakes, so it's at least 1 minus epsilon to the capital M. And on the other hand, it's at most n, which is the sum of all the weights that you start with, times 1 minus epsilon over 2 to the little m. That's the number of mistakes that you make, little m. Why is that? Well, each time your algorithm, this weighted majority algorithm, makes a mistake, at least half the weight gets scaled by 1 minus epsilon. Okay, so that means all the weight gets scaled by a factor of at most 1 minus epsilon over 2. Okay, and you just solve for the number little m of mistakes using these two inequalities, and you get this bound. Okay, this is all standard. Stop me if there are any questions. You can improve this to the randomized weighted majority algorithm, which gets, so the idea behind this algorithm is instead of deterministically following the weighted majority, you sample an expert proportional to its weight, and then you just output what that expert outputs. And you do this on each day independently, your sampling of the weight from that weighted distribution on that day. And you can show the expected number of mistakes made by your algorithm is now 1 plus epsilon times the number of mistakes made by the best expert, again, plus order log n over epsilon. OK. Yeah, so this is all standard classic stuff. That was the weighted majority algorithm that just follows the weighted majority, has this guarantee. And I said epsilon was a parameter. If you set epsilon to be roughly root 1 over t, or I'm going to ignore log factors for the talk, you get regret, which is order 1 over root t. OK? And that's best possible offline information theoretically. Okay? Regret, more precisely, order root log n over t. So the question that we ask, which was actually asked by one of you, is these classic algorithms, they require omega n memory. Why do they require that? Because you're maintaining a weight for each of your n experts. But what if n is very large, and we want sublinear space in n? Okay, and there are applications where n is very large. Maybe these are not people making predictions, but maybe each of these experts might correspond to an algorithm, a potential algorithm you want to explore for some very large optimization problem. Maybe each expert corresponds to a random string that you're trying, and so on. So there are applications where n is very large, and you want to get space sublinear in n. And the question is, what is the space accuracy trade-off for this problem? Okay. Yeah, so we're going to focus on looking at this question in the streaming model. It makes sense since this is a problem of sequential prediction. So this model is on each day, you wake up with no memory, except possibly a note from your past self which has at most s bits. Okay, s is your space. And then what happens is you stream through the n expert predictions on that day. And you make your own prediction. You then see the outcome. You then update this note to your future self. and you fall asleep, and you wake up on the next day. Okay, so that's how this process works. So our upper bounds will. Yeah, question.
You have to like stream over the end.
Yeah, very good. Thanks, Hwa-Chun. Yeah, so the upper bounds will actually work when you stream through the expert predictions, and the lower bounds will hold even if you get to see all the predictions at once, and you just store this in between days. Yeah. Okay. Yeah, so there are different notions of a streaming model. So there's the arbitrary order model, which is an adversary chooses a worst case input for you. Okay, it chooses all the predictions and outcomes on the days, and puts them in some arbitrary order. So that's one model we'll study. This is, I would say, the standard streaming model. We'll also study the random order model. You can think of this model as follows. The adversary does what I just said. It creates these predictions for all days of the experts together with the actual outcomes. And then the days are randomly shuffled. This is one way of thinking of it. So this is a more benign adversary. And it makes sense in distributional settings. Okay, you can think of maybe each expert is, has its own distribution on 0, 1. And each day we get an IID sample from each of the experts. And so then the days are IID, and so they're naturally in a random order. Okay, so that's one way of thinking of that model. Yeah.
So in the first model, the adversary does this without seeing my node.
Yeah, so that's a very good point. So I'll get back to that question later. So the adversary is fixing the input in advance in this model before seeing any of the algorithm's outputs, and definitely not its state. Yeah. Is that?
I wanted to ask basically the same thing. Like, what if the adversary can change the outcome based on?
Yeah, so let me get back to that. I mean, one way of addressing that is to have a deterministic algorithm, and we'll show actually very strong lower bounds that you can't really do anything with the deterministic algorithm. I'll mention that in follow-up work later. But actually, you can do something in terms of an upper bound in that model if you just reveal the output. The prediction of the algorithm in each day, as opposed to disclosing its entire state. I'll also mention that in follow-up work later. Any other questions? Okay. Yeah, so to get a handle on this problem, let's look at some natural ideas. Can we just try to find the best expert and then follow that expert forever? Okay, so that would be a very natural thing to try to do. Unfortunately, this requires linear and n space. And there's a simple argument, just a reduction from two-player set disjointness. Okay, so Alice has this set X. It's represented as this characteristic vector, a subset of n items. Bob has a set Y, and in this, they're talking to each other, and either the sets are disjoint or they uniquely intersect. Okay, this requires omega n randomized multi-round communication. And what is the reduction? So the omega n hardness holds already for 2 days. But you can also make it hold for t days just by copying each day t over 2 times. What is the idea? So Alice is going to create a stream S so that each element of her set X corresponds to an expert that is correct on day 1. And Bob creates his stream S prime so that each element of Y is an expert that is correct on day 2. And you see from the, so the sort of standard streaming simulation to get lower bounds from communication complexity. So Alice runs the streaming algorithm on the stream that she creates, passes the state of the algorithm to Bob, who continues it on the stream that he creates. And if there's an intersection, then that means there's an expert that was correct on both days, right? It was never wrong, or more generally correct on all t days if you do this copying thing I said. And so if you could identify the best expert, then you could you get some index I of that expert, and you can just check if that corresponds to an intersection. Okay, with negligible additional communication. So you solve set disjointness, and so your streaming algorithm needs omega n memory. So it might look bleak, but this is not the end of the story, because a low regret algorithm need not find the best expert. Okay, so think of this instance where I had this two-player communication problem, and Alice and Bob corresponded to day 1 and day 2 respectively. And I copy Alice's input t over 2 days, and I copy Bob's input t over 2 days. Okay, so what I can do as an algorithm, a low regret algorithm, is, well, I just try a few experts until I find one that is all ones on the first t over 2 days. And I just follow that expert for t over 2 days. And I'm right all the time. And then around the t over 2th day, maybe that expert starts outputting 0. It's wrong. And I switch to some other expert that's right for the next t over 2 days. And I'm right on almost all the days, but I have no idea who the best expert is. I don't know if there's an expert that's right on all t of the days. I just followed 2 different experts that were right sort of locally on their t over 2 days, and overall I got low regret. So,
I'm
yeah.
sorry.
Yeah.
I missed exactly where you switched from the streaming to. Were you just arguing about Alice and Bob?
Yeah, so I was trying to, so this was I took this set disjointness communication problem, and I used it to show a lower bound for this streaming problem with just 2 days.
Yes.
It also holds for t days just by copying each input t over 2 times. And I was trying to argue that this instance, well, it's hard for identifying the best expert. But it's not hard for a low regret algorithm, because what a low regret algorithm could do is just find an expert that's, right, because what does the instance look like, right?
But what I'm trying to understand is it are you actually describing now a streaming algorithm, or
I'm describing a streaming algorithm
for Alice and Bob?
Well, I mean, there's no sort of communication game other than the set disjointness thing that I described. So what I'm describing is a streaming algorithm that has low regret.
Okay.
And only for this instance. I mean, in this instance, it looks like, I have the first t over 2 days are copied, right? So it might look like this. And maybe there is some best expert that's right on all t days. But all the other experts, they're either always wrong. I mean, there are some columns that are all 0. And all I'm saying is that, if, as a streaming algorithm, what I can do is, well, I notice this expert is right on the first day. And so then I'm just going to follow this expert for t over 2 days. And then I notice that it starts being wrong. And then I just follow some other expert for the next t over 2 days. And I have low regret, but I have no idea who the best expert is. So all I'm trying to say is that a low regret streaming algorithm need not figure out who the best expert is. Okay.
That's even true if the experts are guaranteed to make vastly different number of mistakes.
So in this case, the experts, well, I'm not sure exactly quantitatively what vastly different means, but this one makes 0 mistakes.
By multiplicative factor of 1 plus epsilon.
I mean, okay, so it will start getting easier if not 1 plus epsilon, but you mean like huge multiplicative factors, or like all ones versus maybe 1, 1 or something, or. But we'll see exactly what a distribution that works. Yeah. So let me get back to that. Okay. So here are our results. We first prove a lower bound. So it's a trade-off. Any algorithm that achieves regret delta less than 1/2, and delta larger than 1/2 doesn't make sense because of random guessing can get that. With probability at least 3/4, say, must use n over delta squared t memory. Okay, so let me put this into context. So remember we said offline, the best possible regret delta was square root 1 over t, up to log factors. And so if you want to get the information theoretically optimal regret, then you need omega n memory. Okay, but this doesn't rule out the possibility if you want a small constant regret, and maybe delta is 1%, maybe you can get memory which is n over t, theta n over t, which can be significant if the number t of days is large. Right? It's significantly less than this omega n memory algorithm that just stores a weight for every expert. Now this lower bound, it holds for both of those streaming models I mentioned. as well as what I'll call IID streams. I won't define that, but you can think of this as each expert having a distribution and taking independent samples across the days. Okay. We show an upper bound which matches this lower bound, but in the random order model. Okay, so I mean matches up to log factors. So we get n over delta squared t memory up to logs for any delta that can go down to the information theoretic minimum up to constant factors. The algorithm doesn't need to know things like the number m of mistakes of the best expert. It doesn't need anything it shouldn't know. It does extend to more general loss functions. So instead of just binary outcomes, if you have a cost vector, but I'm not going to describe that here. So this is a nearly tight bound in the random order model. For arbitrary order streams, we don't have tight bounds. Okay, so this is a nice open question that hopefully one of you can solve. So what it says is that if the number m of mistakes of the best expert is at most roughly delta squared t, and the regret is at least roughly the information theoretic minimum, then there's an algorithm that uses n over delta t memory. Okay, so let me parse this. So if delta is a small constant, again, maybe 1%, this restriction is not so bad, that the number of mistakes of the best expert, it can roughly be as large as t, the number of days, up to log factors. And in that case, what we would get is n over delta t memory. Delta is a constant, n over t memory. So that's still significantly sublinear. And if delta, if you want to get regret close to the information theoretic minimum, so delta is 1 over root t, then it's saying, well, we need to restrict the number of mistakes of the best expert fairly severely. Okay, it needs to be polylogarithmic. But under that restriction, we still get n over root t memory, which is still significantly sublinear. And you might be looking at this and thinking that this upper bound contradicts the lower bound that I just said. Right? I said there's an n over delta squared t lower bound. Delta is less than 1. But it doesn't contradict that because we have this assumption that the number of mistakes of the best expert is not too large. Okay, so what that reasoning shows is that actually the hardness in the lower bound is coming from the best expert making a lot of mistakes. And you can actually show an n over delta t lower bound for this regime, but you could hope to have this regime, this lower bound hold even up to m equals delta t over polylog n. Anyway, there are open questions here that are not resolved.
Actually, a lot of mistakes, like a lot, but not too much, because then I can just guess, right?
Yeah. So yeah, the best expert, the hardness is actually going to come from the best expert making, roughly t over 2 minus delta t mistakes. Yeah. So close to t over 2, a little bit better than guessing, but parameterized by this delta. Any questions? Okay. Yeah. So let me just go over the techniques. Let me start with the lower bound. So again, this is an n over delta squared t lower bound for regret delta on the memory. And we're going to define a communication problem and use it as a lower bound for streaming. And I'll call this a distributed detection problem. So the notation is epsilon diff dist. And here's what the problem is. You're going to have t communication players. Okay, so the players are not corresponding to experts. The players are corresponding to days. Okay, so each of the t players is going to hold an n-bit string. Okay? These n bits, these are the n predictions of the experts on that day. And they must distinguish between two cases. There's a no case where every bit of every player is an independent fair coin toss. Okay. More interestingly, in the yes case, we select an index L from 1 to n arbitrarily, and the lth bit of each player, again, you might want to think of this as, oh no. Sorry. Okay. It's gone. Okay. Oops. Okay. Yeah. So you should think of this as a matrix. Again, the columns correspond to the n experts. The rows correspond to the t days. That's what will be in the reduction. But in this communication problem, each row is one of the t players in the communication game. And each player has the n predictions on that day. Okay, so this is a distributional problem. The no case, all the entries in this matrix are independently uniformly random. And in the yes case, we choose a column L, and we put a biased bit there. Okay, so here's the lth, lth column, and this bit is more likely to be 1. And so, and all the other columns are uniformly random. So in this lth bit, the parameter epsilon is involved, so the bias from a half is epsilon. Okay. So we're going to look at the Blackboard communication model. These players post their messages to the Blackboard. For the application to the experts problem, we actually only need the one-way model where the first player posts, then the second player sees the post, and so on. But the lower bound actually does hold for multi-round communication. Yeah, so this is just the picture. This is the no case. And in this yes case, I have this planted coin.
So sorry, about the model, the players have no information about the inputs of the others except what's written on the board?
That's right, yeah. So it's Blackboard communication. One round is enough. You can just think of them posting on the Blackboard in order. The final player is going to output the answer. Okay, so a natural protocol for this problem is to choose 1 over epsilon squared players, say the first 1 over epsilon squared players, 1 over epsilon squared times log n, and just have all the players communicate their inputs or post their inputs to the Blackboard. And that's enough to distinguish a biased coin, right? So I need 1 over epsilon squared samples to distinguish a fair coin from a biased coin, and I can union bound with an extra log n. And so there's an upper bound of n over epsilon squared. And what you can show here is that n over epsilon squared communication is necessary. And you should think that this is a natural bound to expect. I mean, again, we need 1 over epsilon squared samples to distinguish between a fair coin and one with bias epsilon. So that's kind of like one column of this matrix. And the intuition is the players roughly need to solve this single coin problem on each of n columns. Okay, it's not precise because really what they're solving is the OR of the n columns, but that's just as hard. So formally, the way to prove this is using information complexity. So we can measure information when the coins are all drawn from the no distribution. So they're all independent, identically unbiased. And we can use a direct sum theorem for OR of Bar-Yosef et al., maybe building upon earlier work of Chakrabarty et al., to show high information costs under this no distribution for a single coin. So this direct sum theorem will say that to solve the OR of these n copies, it's the information I reveal under the no distribution is n times the information I need to reveal for one of these copies. And for one of these copies, how do you show a lower bound? So you can show a 1 over epsilon squared information cost lower bound for this single coordinate problem, distinguishing a fair coin versus one with bias 1/2 plus epsilon. So the correctness guarantee on that column is, I have either a fair coin or a coin with bias epsilon. It's distributional, so I'm trying to figure out if I'm in the first case or the second case. And the information is measured with respect to the uniform distribution. And so here you can use a strong data processing inequality. Ducci et al. Had the first argument for this to show a 1 over epsilon squared lower bound for that problem. This was extended to higher dimensions and put in the direct sum framework, sort of the standard framework we're familiar with by Garg et al., and extended to sparse parameter estimation that I won't talk about, Braverman et al. The rough idea here is, so again, using a strong data processing inequality. So the samples, you can think of, you have a bit which tells you if I'm unbiased or if I have bias epsilon. And I'm seeing samples from that distribution. And you have a Markov chain here where you have a bit, you have a sample, and you have the protocol. And the information the protocol reveals about this bit, it's at most the information the protocol reveals about the sample. That's sort of the Markov chain property. That's sort of the standard data processing inequality. But in fact, the information is much less. That the information that I reveal, like I have this bit which tells me if I'm going to sample from either the uniform distribution, so Bernoulli 1/2, or from a distribution which is slightly biased, 1/2 plus epsilon. And I take a sample from that distribution, and I have a protocol that's the input to the protocol. I have a protocol that processes these samples. And I look at the information that this protocol, the transcript of the protocol, reveals about the bit. By sort of standard data processing inequalities, I can say that it's, I have a Markov chain here. And a strong data processing inequality would say, oh, well, it's actually much less. Okay, so that's what we use here. That you can think of Z not carrying much information about B at all, because Z, you can think of it as these two distributions are very close. It's a very noisy representation of which distribution it came from. And so this is what is meant by a strong data processing inequality. Plugging this into this direct sum framework, you can show a 1 over epsilon squared lower bound. I just wanted to give you sort of the high level. Yeah.
That thing, is that in your paper or is that from somewhere else?
No. So this is old. This is a binary symmetric channel. I think this is an Ashwald, very old work. This technique was used in Ducci et al. In fact, in all of these works. Yeah.
So the lower one holds for any t, does it depend on the number of points you have, the number of players?
No, this is a 1 over epsilon squared lower bound for any t. Yeah. Throughout, for us, t is going to be at most n, just for the, I think our problem, yeah. But I'll actually mention when t is larger than n later in the talk, yeah. Okay, so by using this in the direct sum framework, you can get an n over epsilon squared communication, even information lower bound for this problem. Okay, so, but how do we use this communication problem for our streaming problem? Okay, so yeah, the intuition that I alluded to is that each of the players is going to correspond to a day. And there's some column that has maybe a little bit more ones than the other columns. How can I use that as a streaming lower bound?
You could use the slide.
What's that?
I said you could use the idea on the slide.
Use the idea on the slide, but there is a problem. Does anyone see a problem? Like, what was the problem for two-player set disjointness? I mean, if I just have this as my matrix and I need to predict something on each day, what would you predict without looking at the matrix? You would predict 1, right? I mean, who cares what's going on here? There's some column that has more ones than not. So let me describe it on the slide here. Right. So what we're saying is, these are the experts. These are the days. And maybe there's some column, let's say this column, that has a little bit more ones. Maybe not, but there could be. So why don't I just always output 1? Right? Then, if the actual outcome is 1 on every day, and the best expert is being right, has is a biased coin, so has t over 2 plus epsilon t ones, then I'll be pretty good, right? I'll be as good as the best expert. And I learned nothing about the communication problem. I didn't solve it, of course. So how can we fix this? So we would like to use an online learning with experts algorithm for solving this communication problem, where the epsilon parameter is going to be roughly the regret, delta. But a good algorithm exists if it just outputs 1 on every day. I mean, if we're defining the outcome to be 1 on every day, and we're saying that there's a coin that has slightly more ones, so we can fix this with a masking argument. So the outcome on each day is masked by an independent fair coin flip for that day. And the expert advice is also flipped on that day. So here is the picture, right? So here is the setting, the experts, the days. And you would just predict sunny on every day, because the actual output is all ones. But instead, what we can do is we can have the communication players hide information from the streaming algorithm. What does that mean? Well, the first communication player, this day 1, will choose a mask, a random bit, which is 0 or 1. And it'll flip all of the predictions by that mask. And the actual outcome, instead of being 1, will be 1 XORed with that mask.
So aren't you just saying that the actual inputs in the disjointness are whether the expert is correct or not, instead of what the expert says? And then you just choose like a random bit so what's the truth? And then the bits in the communication just say whether the expert is correct or not.
So what you want to say is, yes, so say it again. You want to define an outcome on each day, so that what happens?
Right, then that's what I was understanding. So the input to the disjointness is just, or the hard instance for the disjointness,
Yeah.
the biased point,
Yeah.
says whether the expert is correct or not. And then now the mask will tell you the reality, right? Or maybe.
Well, it's important that I mean, so there's an expert here that's right. Maybe
1 plus epsilon.
1/2 plus epsilon of the days.
Right, exactly. So one says that the guy is correct.
This is a yes instance, yeah. And no instance, everything is truly random. Okay.
I think
Sorry.
the question is just this corresponds to whether it's correct or not, but it doesn't correspond to how the experts predict whether it's 1 or 0. Right?
Yeah, what is the actual input that you're giving the experts? I mean, giving the players. So these correspond to the inputs of the players themselves, right? I can describe this, and maybe you can tell me if it corresponds to what you're saying. Yeah. Okay. So I flip. I'm the first player. I'm going to choose a random mask. Maybe I choose it to be 1. I'm going to flip all of the n bits, which are the n predictions for the experts on that day. I'm not going to tell the streaming algorithm how I flipped it. I'm going to run the streaming algorithm through these. And then the streaming algorithm makes its prediction, sees the actual outcome, goes on to the next day. The next day, I independently choose a mask. Here, the mask is 0, so these didn't get flipped. I run the streaming algorithm again. At the end, I reveal the outcome, and I go on to the next day, and so on. OK, let me describe the important properties here. So if I'm in a no instance, what does the input look like?
Same. Right.
Yeah. So all bits, all predictions of all experts are independent fair coin tosses. But not only that, the outcome is also independent and random, right? Because the mask was just this independent bit chosen by the communication player and hiding it from the streaming algorithm. So all bits and all outcomes are IID Bernoulli 1/2, right? Which means any algorithm, so all the experts, there's no good expert, first of all, right? Like the best expert is, just by turn-off bounds is going to be right, like, around t over 2 days. And there's no algorithm that does better, right? I mean, everything is independently random. OK, so that's one nice thing about the no distribution. What happens in the yes distribution?
There's one expert that's correct.
In the yes distribution, the masking didn't change the number of times the best expert was correct, right? So there's still a good expert there.
Oh, because you mask the outcome as well?
Yes.
Oh, okay.
Yes, we mask the predictions, and we use the same mask for the output. Yeah.
Is it here in the no distribution, it's not enough that no expert is good enough?
It's no algorithm is good.
Yeah,
Yeah,
no
exactly.
algorithm.
Yeah, exactly. Yeah. Nothing can predict well in this case because all of the bits are independently random. Okay. So let me formalize that. So yeah, here's the no case that was just asked about. If there is no biased coin, no expert and no algorithm will do better than t over 2 plus, say, t delta over 3 days. That's just by turn-off bounds. On the other hand, in the yes case, there is a good expert because you're in this yes distribution. And so if you have low regret, you better do pretty well. You can't do much worse than that best expert. And so you're correct with at least t over 2 plus 2 delta over 3 days, whatever. There's a gap here. You can distinguish them. And you can keep track of how many times the streaming algorithm got it right and use that to figure out, from a communication game standpoint, if you're in the yes or the no case. OK, so that's the idea. How much time do I have? Is it almost?
I think like
7 minutes. OK. Yeah, let me just. OK, so to summarize, you can use this streaming algorithm to solve this communication game, which requires n over delta squared communication. And so between 2 consecutive players, you're passing the state of the streaming algorithm. You have an n over delta squared t memory lower bound. OK. What about upper bounds? Is this anywhere close to upper bounds? So let me give some quick intuition here. Let's first look at the no mistake regime. OK, there's an expert that never errs. What is a natural algorithm here to achieve sublinear memory? Well, something natural would be to, say, pick the first some number of experts and just run one of these classic offline algorithms on that subset of experts. And if they start doing really poorly, then throw them all away and choose the next block of experts. If they start doing poorly, throw them away, and so on. OK, so let's see how that works when there are no mistakes. Yeah, so the idea I just said is you follow these experts. Maybe I'm just doing a deterministic algorithm right now. I follow the first 2 experts here for the first 2 days. I'm not satisfied with them, so then I switch to the next 2 experts. So if I iteratively pick a pool of the next k experts, and inside of that pool, I can imagine, say, running this weighted majority algorithm or other algorithms for this problem. If I run the weighted majority algorithm, and well, not even the weighted majority, I just delete an expert when it's incorrect. Okay, so I'm in the case where I know there's an expert that never makes a mistake. Then to throw away all the experts in a pool of size k, I'm only going to have log k errors. Right? Each time I error, I throw away half of the remaining experts. Right? So I can only do that log k times until I'm left with no one, and then I need to choose a new pool. Okay. Well, I want to eventually find this best expert. And if my pool size has k experts, then I need roughly n over k pools until I'm guaranteed to include the best expert in one of the pools.
Why, David, why are you throwing half of them away? Are you assuming that?
What
are we assuming now?
Sorry. So I'm just saying, this is just a toy algorithm where I'm going to choose a pool of experts, and I'm just going to look at the majority vote of those experts. And when an expert is wrong, then I'm going to throw them away.
Right, but why can't most of the experts be correct up until the very last? Like what?
Oh, that's fine, right? Then I'll have low regret. I don't need to find the best expert.
Okay.
But if everyone is right until the end, then I did great. And then yeah. This is a simple algorithm where I'm just saying, take k experts, and whenever someone is wrong, throw them away. You won't throw away the best expert because you're in the no mistake regime. And every time you make a mistake, since you took the majority, then half of those guys are thrown out, right? So you have log k errors on a pool, and you could have potentially n over k pools until you get to the best expert. You want to make a total number of mistakes of delta t. So you just solve for k. N over k times log k equals delta t. And you get a pool size which is roughly n over delta t. Yeah?
Soon after you throw away half of the experts, can you just fill in the new ones so that?
Yeah, you can do. You could do that, but.
You get some better dependence on log.
Oh, on log. Yeah, that's a good suggestion. We haven't tried to optimize the log factors. Yeah.
Can you repeat the suggestion?
The suggestion was, what if I just immediately, suppose I throw away k over 2 of the experts, then just put in the next k over 2 immediately. Maybe this could help for improving concrete factors, like log factors. It won't improve more than logs, because there are lower bounds, but for deterministic algorithms that I'll mention. Okay, so this is your space, right? The pool size is how much memory you use. You just maintain those people in your pool. Okay. Yeah, and going back to Omri's question, yeah, so if the number of rounds is small, then the pools must have done well, so my regret is small. And the number of rounds cannot be large because at some point the best expert would have been chosen, and since we have no mistakes, it would also be retained. Okay. What about a low mistake regime? If the best expert makes m mistakes, the same idea would work, where I use a pool size which is a factor m larger, because I'll cycle through all the experts m times, and after that I can't throw away the best expert again, because it only makes m mistakes. Solving for the pool size, which is the memory, you get nm over delta t. But this is not a good bound, right? I mean, m can be very large. M can be up to t. Right. OK, so a natural idea instead is to try to randomly sample the pools of experts instead of iteratively picking them. One issue here, though, is you cannot guarantee that the best expert will be retained. In fact, this is a major issue, right? Like, you might sample the best expert at some point, but it makes a lot of mistakes in that region of days around when it's sampled, and you throw it away. And then you might have to wait a long time until you sample that expert again, or maybe you won't sample it again. Right, so we still have this intuition that if the number of rounds is small, the pools must have done well. Otherwise, we hope to sample and retain the best expert. Those are sort of the two things we're trying to make happen together. the algorithm is what I just said. It's very simple, right? So repeatedly sample a pool of n over delta t experts. That's what I want my memory to be. So that's the pool size I'm going to sample by. And I'm going to output the majority vote of the pool. And I'm going to decide to delete any expert that has bad accuracy. Okay, so I can look at how many mistakes it's made since I got it. And if it has accuracy roughly less than 1 minus delta, then I'm going to discard it. Okay, but the distribution here actually, the distribution here is fairly complicated, right? Like, what days am I going to sample experts on? It depends on the entire history. Maybe I made some samples in the past that caused me to throw away my pool here, and so on. So it's hard to understand this distribution. But let me just give you, since I'm over time here, let me just give you the slide of intuition, which is that these x's, so these boxes here correspond to days. These x's are days where the best expert made a mistake. These yellow boxes around the x's, these are days where if you were to sample the best expert on that day, you would throw them away. Okay, because they didn't make a mistake on that day, but I'm going to keep track of how many mistakes they've made, and I notice right here, oh, they've made so many mistakes that I'm going to throw it away. But you can't have many yellow boxes either. Right? So the idea is, well, in this arbitrary order model, we're restricting the number m of mistakes of the best expert to not be too large. And the number of bad days, sort of days where the density of mistakes of the best expert is large, is only a 1 over delta factor larger than the number of mistakes it makes. And so as long as we have a number of times we sample in the stream, which is larger than the number of bad days, it's significantly larger than the number of bad days, we will sample the best expert on a good day, and we will retain it. So that's how the argument works for the arbitrary order model. And the intuition behind the random order model is that the local behavior of the best expert looks like the global behavior of the best expert, right? So like you don't have sort of regions of high density of mistakes, right? Like if the best expert makes some total number of mistakes, then in any sort of small region, it also makes that rough same number of density of mistakes. And that's what helps us get rid of this assumption that the number of mistakes of the best expert is small in the random order model. Okay, so that's all I'm going to say about this in the interest of time. Just to conclude, to summarize, we showed this n over delta squared t lower bound. It's a trade-off between regret and memory. We showed a matching upper bound in the random order model up to log factors. For the arbitrary order model, if the number of mistakes of the best expert is not too large, then you can get sublinear memory. Natural questions, the natural question type bounds for arbitrary order streams. Also, the ideas behind multiplicative weights are used for many other tasks. How general is this framework? Can you get streaming algorithms for other problems in optimization? There's some follow-up work. So one thing that we can, this is just a manuscript still being written, but one thing we can show is that any deterministic algorithm must use omega n bits of memory to achieve constant regret. Okay, so, and more precisely, it seems like the following goes through, though we're still verifying it, that you can show if the best expert makes m mistakes, then there's an nm over t lower bound for deterministic streaming algorithms. And that actually matches this very simple idea of walking through the all the experts m times that I mentioned, taking a pool of size nm over t. So deterministic algorithms, there isn't much you can do, and the bounds seem to be tight. But going back to a question about the input model, oftentimes in online learning, you want to allow the adversary to choose the input as a function of the predictions made by your algorithm. And our algorithms are randomized, the ones that achieve good bounds, and they don't allow this. Okay, so it's if I reveal to you my state, I told you which experts I sampled. There might be a way for the adversary to try to make it hard for me to try to make me have many pools, sample many pools of experts. I mean, our proofs would just break down. Like we don't have any argument there. But one thing we can show is if we only reveal our outcomes to the adversary, not the internal state, then we can get an upper bound of n over delta root t. Okay, this is in the arbitrary order model where I said there's an n over delta t upper bound if the number of mistakes is not too large. With those same conditions, we can get n over delta root t memory and handle an adversary that can choose its inputs as a function of your outcomes. And this uses ideas in differential privacy to take multiple copies of the randomized data structure and output a private median of the copies where the output is the prediction. But I can answer questions on that if you have any. And finally, in very interesting follow-up work of Peng and Zhang, they consider the case where the number n of experts is much less than the number of days. And so now they're allowing, so they want memory which is sublinear in n again. They get n to the delta memory where the number of errors they get is t to the 2 over 2 plus delta up to poly n factors. So here n is much less than t for any delta in 0, 1. So it's interesting, right? Because if if I set delta to be 1/2 or something, any constant between 0 and 1, I'm getting sublinear memory and I'm getting regret, which is I'm getting a number of errors which is much less than t. But on the other hand, there's something suboptimal about this result, right? Like you would expect when delta is 1 to recover the full information offline algorithm. This should be t to the 1/2, but they're getting t to the 2/3. Okay, so this is this one is on archive. This one is available. Yeah, so that's all. Yeah, thanks.
So for the random order thing you mentioned, the upper bound you mentioned, so does it only require the best expert to do random order?
Yeah, it needs. I think that's right. Let me remember this. Yeah, the main property we need is when the best expert is sampled, it's retained. So I don't think we need any. Yeah, and I need to page it back in, but I don't think we need any other assumptions on the other experts. Yeah.
More questions to David?
Yeah,
so
Stefan.
when you want to use this in convex optimization, your expert will be constrained. Let's say multiplicative weight update, your expert will be constrained.
Yeah.
You solve an oracle, and then based on that, you decide to update the weight. So basically, it seems very adaptive, Like, in the sense that your output is like your input in the next stage is like a deterministic function of your output.
Yeah, I mean, so that's good motivation for getting bounds for adaptive algorithms. But there are already issues with that. Like if you try to solve linear programs in the standard way here, you would need to update all the constraints, or you would need to get lucky and sample the D constraints that determine the optimum, right? Like the algorithm here doesn't even work for say solving LPs with multiplicative weights. So it's like some of those reductions need access to all the experts in every day, and
For the oracle, you mean they need that, or?
Yeah, I mean if you don't have all the you want to touch all of the constraints in your LP at each time, and you don't have them. You stored a random sample of experts in this algorithm.
Like for
And,
example, right,
yeah.
in Madri's multi-commodity max flow, sub-problem you need to solve is the shortest path, right? And just to solve that, before you even update the weights of the experts, basically decrease the weights along the shortest path, right? Just to solve that shortest path, I don't think it makes sense to solve that with sublinear memory. Is that what
You
you're
are saying I don't know the weights of the graph that I want to compute.
Yeah, I don't think it makes even sense to solve the main problem is not the space you need in order to, I guess I'm saying the main problem that you need to solve, like APSP there, in each iteration, that I don't think it makes sense to solve it using sublinear space.
Yeah, I mean, for LPs, it wouldn't make sense to sample n over k constraints and then just sort of have weights there. Like it wouldn't. You're trying to find k constraints that witness a.
Yeah, but like Clarkson algorithm, for instance, is doing that
Oh,
for low dimensional.
Yeah. So. Well, no, I mean, what do you mean exactly? I mean, it is maintaining weights for everyone, right?
All the constraints, or you just?
I mean,
I mean, it's correct. You're maintaining weight for all the constraints, but
Right.
you sample a small number of them and work with that a small sample at each iteration.
but you need to keep the weights around, right, for all the constraints.
Your technique is saying that.
This technique is sampling a subset and only keeping weights for that subset. Right, otherwise the memory would be too large. Yeah, I mean, it'd be interesting to see if there's some way of doing it, but I don't immediately see any. Yeah.
So like the problem is not just adversarial robustness.
That's right. That's right. Yeah. Exactly. Yeah.
Great.
Thanks.
So let's